In this video we're going to talk about scientific notation representing very small numbers. In the last video I talked about scientific notation representing very large numbers. So if you want to see that, you could go check it out. So let's just review the basics of scientific notation. Scientific notation is going to be in the form of some number times 10 to a power. And this number right here has to be between or including 1, but strictly less than 10. So somewhere between 1 and 10, but it could be 1. So let's take a look at an example of a very small number using the calculator here. Let's clear this. Let's say we wanted to do 1 over 5 million. So 1 divided by, and you could do this on your calculator too, divided by 5 million. So that's a 5 with 6 zeros. 1, 2, 3, 4, 5, 6 equals. Alright, so my calculator gives me this. Now, like I said, you should do this on your calculator to see what your calculator looks like. Mine has a e -7. Some of them will have times 10 to the -7 or other forms of scientific notation. But this means that the calculator is giving me the answer in scientific notation, which is the same as what I talked about in the last video with very big numbers. The difference here is there's a -7 or a -7 and not a +7. Now all these zeros right here don't really mean anything. 2 decimal and a bunch of zeros. So I'm going to transfer this to the other board, but I'm not going to write all those zeros. So the answer we got when we did 1 divided by 5 million, or 1 over 5 million, same thing, is 2.0 times 10 to the -7. My calculator said 2.000, a bunch of zeros, and then e -7. What that means is times 10 to the -7th power. Why does the calculator do this? Well, it does this because it can't fit all of the digits on its screen. Most calculators are programmed to go into scientific notation if you can't fit all the digits on the screen. And that is the purpose of scientific notation, to represent very small or very large numbers it's hard to write it all out with all the zeros. So if I write this little abbreviated version here, I can represent the number the same way without writing out all the zeros. So let's talk about what this means. If you didn't watch the video on very big numbers, you probably should start with that. The difference between the very small numbers and the very big numbers when I punch this in my calculator is my exponent here is negative. And when my exponent is negative, it's telling me I have a very small number. If my exponent was positive, I'd have a very big number. Since the exponent is negative, if I want to write this number out the long way, I'm going to have to move the decimal to the left. Think of it towards the negatives on a number line. So I'm going to take this 2.0. I'm going to start with 2.0 if I want to write this out the long way, and I'm going to move the decimal 7 places to the left. So once around the 2, and then I'm going to have 6 more places to go. 1, 2, 3, 4, 5, 6, and that's where my decimal is going to be, and I would fill in the rest of these with zeros. So my final answer would look something like decimal 1, 2, 3, 4, 5, 6 with a 2. And that's the same as 2.0 times 10 to the -7th power. So this is a very, very, very small number. You could also put a 0 out here in front of the decimal just to reinforce that this is a decimal number. Although with all these zeros, it certainly does look like it. You see this 0 here sometimes. It's the same as if you don't have a 0. That 0 doesn't really count as far as when we're moving our decimal. Alright, let's look at another example of a very small number. Let's see here. I found this. It says, what is the width of an atom? 1/millionth of a millimeter. Okay, how could we write that in scientific notation? 1/millionth of a millimeter. 1/millionth of a millimeter. Let's do that without the calculator. So to do this, we need to think about our place values. 1/1 millionth. I could write that as a fraction. 1 over 1 million. 1 million. A millimeter is like super tiny. It's probably about the width of that line right there is a millimeter. So 1/1,000,000th of that width of that line is what they're talking about. That's very, 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 very small. To write it in scientific notation, I really need to get the decimal. And we could use our calculator to get the decimal. We could go 1 divided by 1,000,000. 1, 2, 3, 4, 5, 6 equals 0.000001. There's actually 5 zeros there. But I do kind of want to talk to you about how you would get this without a calculator, and we can write this down and then talk about it. 1, 2, 3, 4, 5, 1. The way you could get that without a calculator is remembering your place value. This place value here is the tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So this decimal represents 1/1,000,000th, and here's the fraction for that. So to write this in scientific notation, what I would need to do is move my decimal back to the right so that this number in the underline area is between 1 and 0. In this case, it's going to be 1. So let's move that decimal over. 1, 2, 3, 4, 5, 6 places, and then my decimal would go right there. So to write this in scientific notation, I would have 1 times 10 to the -6th. Because it's a very small number, I'm using the negative exponents. There's actually an official definition for negative exponents, and it has to do with fractions. And I think for this video, I'm just going to skip that, and we'll maybe talk about that negative exponents in another video. But what you could know, I guess, is that 10, we know 10 to the second power, it means 10 times 10, right? And that is 100. 10, that's not a 10. 10 to the first power is just 10. That's just 1/10. That's just 1/10. 10 to the 0 power is actually 1. Anything to the 0 power is 1. Then 10 to the -1 power means 1 over 10. And 10 to the -2 power means 1 over 10 times 10, which is 1/100th. 10, why do I keep doing that? 10 to the -3rd power is 1 over 10 times 10 times 10, which is 1 over 1,000. So negative exponents are defined as reciprocals. 10 to the -3rd is the reciprocal of 10 to the 3rd. 10 to the 3rd is 1,000. 10 times 10 times 10. 10 to the -3rd is 1 over 1,000. So that's why we have these very, very small numbers with negative exponents, because they represent fractions, very, very small fractions, like 1/1000th. 1/1,000,000th is 1 times 10 to the -6, because 10 to the -6 is basically 1/1,000,000th. Now, you don't have to know all that to know how to write something in scientific notation. I mean, you can simply remember that very small numbers are going to have the negative exponents and very large numbers are going to have the positive exponents, and you'll be fine. But it is kind of good to understand what negative exponents mean, as if you go on in algebra, I'm sure you're going to come up against some negative exponents in the future. So let's do another one. Let me just make one up, and let's write it in scientific notation. Let's say I have the very small number 0.000375, and we want to write that in scientific notation. If you feel comfortable, you might want to just pause the video and try this by yourself, and then start the video when you have your answer and see if you have it right. Okay, so to put this in scientific notation, I have to move my decimal until I get a number that's between 1 and 10, and that would be right there. It would be 3.75. So how many places would I have to move the decimal here? 1, 2, 3, 4. 4 places this way, so that's going to mean -4 is going to be my exponent, because I have a very small number. So in scientific notation, this would be 3.75 times 10 to the -4th. You're always filling in this blank, 3.75, and then this exponent to the -4. And the rest of the blue part is always going to stay the same. That's just the format of scientific notation. Okay, let's try a couple more. It's always good to do more examples, I think. Let me erase this. Let's do another one like that, where I give you the very small number and you write it in scientific notation. Okay, here we go. 0.00000, 5 zeros, and then 1, 1. If you want to pause it and try it. Okay, so how many places? 1, 2, 3, 4, 5, 6. Stop. You're always going to have just one digit to the left of the decimal, one non-zero digit to the left of the decimal. So that would give me 1.1 times 10 to the negative, however many places I moved it, 1, 2, 3, 4, 5, 6. 1.1 times 10 to the negative 6. Let's try one where I give you the scientific notation and then you write it out the long way. So in scientific notation we have the number 2.83 times 10 to the negative 4. How would you write that out the long way as a decimal? Well, we know it's a negative exponent, so it's going to be a very small number. That means I'm going to move it this way to make a very small number, and I got to move it 4 places that way. So it's going to be once around the 2, and then I'm going to have to go 3 more places. So that's going to give me 3 zeros, not including that 0. So 1, 2, 3, 2, 8, 3. My decimal was right here, and then I moved it 1, 2, 3, 4, and that's where it stops because of the negative 4. Well, hopefully that gives you an idea about very small numbers, using scientific notation for very small numbers. So just to kind of finish up what we were doing with scientific notation, I found this interesting representation of very small and very large numbers. So it starts off with 10 to the positive 23 meters. So this is a positive exponent, so it's very big. And where that puts us is 10 million light years away from the Milky Way. So I'm going to start this, and on the top here it tells you what this distance is representing. So 10 to the 23 meters, which is also represented of 10 million light years, is how far we are right here. We're looking at away from the Milky Way, and it's going to start zooming in. So I'm going to start this. So it's zooming in now. So now we're at our galaxy. We're at the Milky Way galaxy. See, this is changing. This is 10 to the 19th. Now it's 10 to the 18th, 10 to the 17th, and we're getting closer and closer to Earth. We can start to see the sun here. The sun is growing larger. There's our solar system. Okay, let's stop it. So now we're 10 to the 13th meters. A meter is about a yard, like a meter stick. So 10 to the 13th meters is 10 billion kilometers. There's 1,000 meters in a kilometer. You don't have to know all that, but it's kind of showing you what these big numbers represent in the scheme of things. So now we can start to see our solar system if we're 10 to the 13th meters away from the Earth. So we're going to get closer and closer here. Now we're getting up to Earth's orbit, and we can see the Earth. Okay, so now we're 10 to the 7th meters, and we can away from Earth, which is 10,000 kilometers, and we can see the western hemisphere of the Earth. 10 to the 5, we're going to Florida, it looks like, Tallahassee. Okay, I'm going to stop it right there. So 10 to the 1st meters, and it's converted it over here to meters. 10 to the 1st is just 10, so we're 10 meters away from the Earth. A meter is about a yard, so we're about 10 yards or 30 feet from the Earth now, and we're hanging at the top of an oak tree. That makes sense. Okay, we go in one more. Now we're at 1 meter, 10 to the 0. Anything to the 0 power is 1, and we can see this oak tree. We're about 3 feet away from the Earth. We're in the branches. Now we're going to start zooming in on this leaf. So we're going to go to negative exponents now. We're at 0 exponent. We were at positive exponents. Very big numbers. Now it's going to start to go to negative exponents, which means we're going to go to very, very small numbers or very, very small distances. So we're going to zoom in on this leaf and get down to atomic level here. We're on the surface of the oak. Magnified 1,000 times. Now we're looking at the cells on the leaf. Now we're looking at individual leaf cells. Now we're looking at the nucleus of the leaf cell. Now we're looking at individual DNA strands, DNA building blocks. Getting down to atoms and electrons now. Empty space between electron shells. This is all science stuff, right? Carbon atoms. Notice we're down here to 10 to the negative 15th power, 10 to the negative 16th is as far as it got. So that's kind of a cool little thing that takes you from all the way out to outer space, all the way into the very tiniest levels of atoms, and a representation of very big and very small numbers, and how 10 to certain powers can represent those very big and very small numbers. I hope that helps you understand scientific notation and how it can be used to represent very big and very small numbers.